So, turns out that when you actually want to sort of apply these abstract regularization things, you kind of want to first write down the proof as if we didn't have the abstract regularization things and we're just utterly careless about transversality. So you kind of want to write down the proof that we had, or the style of proof that we had, and then we'll go in and sort of spruce it up. But you kind of need that outline first. And so there's actually not going to be any abstract theory today either. Instead, I figured I'd give you a real good primer on the Morse trajectory spaces, which you don't really need for the dream proof, but the structure that we're going to put on that is going to be awfully useful certainly when we go to the polyfold world. Then I'm actually going to define all the modular spaces of curves that we want to look at. We'll look at the dream proof, hopefully. And then the next step is to sort of look at the nightmare of what can go wrong with that. So, let's see. So you may or may not have seen this whole Morse trajectory story. I just figured it's good to sort of get us all on one page. So M now could be any compact manifold. It's going to be a symplectic manifold in the end, but yeah, take a function and a metric on it. That pair is called Morse-Smale if there are two conditions. First condition says I want the flow near critical points to locally look like this, which will follow from having all the critical points non-degenerate. So non-degenerate means if you look at the Hessian as a map from tangent space to cotangent space, or tangent space to itself, it's bijective, or surjective, or injective, right? It's all equivalent in finite dimensions. That's Morse. And then the Smale condition actually has something to do with the metric. Whenever you have, so the metric gives you gradient flow lines, or write unstable and stable manifold out in more detail, but you'd like the unstable and stable manifold to intersect transversely. That's what people usually say. The problem is once they intersect, they'll always intersect in the whole flow lines. Right? So they won't ever just intersect in a point, they'll intersect in at least one-dimensional things. And so that is not going to look really transverse in M. Instead, what you do is you take a level set between the levels of your 2 points. Right, so if you take that to not lie in the critical values, then the pre-image, so F inverse of V, will be smooth submanifold, and you should get spheres from both of the stable and unstable manifolds in there, and those you want to intersect transversely. So that's a condition on the metric. You know, there's a theorem that says given a Morse function you can find a metric, so you'll get this. So this is about how sort of globally these things intersect, and let's see where that picture here comes from. Right, so first thing is, right, I already said that if you have a non-critical value now, the level set is going to be smooth, right? That's what we call level set. And the second, that's sort of the Morse lemma that says at every critical point you actually find a neighborhood that splits in which the flow looks like this. And by looks like this, I mean the gradient f. So there's a splitting, gradient f maps. So at a point x comma y, you know, I need to say what the vector is. And I believe in this case I have what? At x equal to 0, I have y negative. Okay, x minus y. So, well, what happened here Oops. Oh no, my trick. I had this beautifully, fully rescaled node here, but apparently they got ungrouped. There we go. So this splitting here is, right, so I can look at my Hessian at the point P. It's going to have, well, it's non-degenerate, so it means it has no zero eigenvalues, so and it's symmetric, so I can split it into positive and negative eigenspaces. Then, of course, the eigenvalues in general will not be plus or minus 1, but the idea is to somehow rescale so that the eigenvalues become plus or minus 1 in those directions, and then to somehow trivialize that nearby. So, question, yeah?
Isn't the last condition the same as WPU intersect WS?
Well, see, is that equivalent? Do they span everything in M? Of course they do span everything in M, right?
Yeah, because they are transverse to F inverse flow.
Right, right, the flow is transverse to that, right. Why is, okay. Okay, yeah, good. So the remark is we don't actually need level sets if we do transverse intersection in M. Right, so that's equivalent. The problem is later on I would then want to, right, so this, I then have to argue that R acts on it. And in order to get from the images of the trajectories to the sort of set of trajectories, I would have to quotient by that R. Right? And so then I have to sort of again, prove that that action is proper and smooth and and free, and I'd like to not have to do that. But yes, sorry, we can, right. Transversality was not the reason that I wanted to go into the level set. It was that I want to get the space of trajectories and not the actual intersection points. Well, yeah, we'll get there. Good, right. So that was equivalent sort of to, right. Yeah. So this local picture, in general, that whole trick with rescaling and making the eigenvalues plus and minus 1 works, but you have to sort of conjugate your flow with just a homeomorphism, apparently. So there's a C0 chart here, which we might not really like to deal with. There's a little extra remark here. We're going to want to have things smooth eventually. There's some notion of a Euclidean Morse-Smale pair that will give you this smooth chart with that special flow. And that's essentially, right, so the Morse lemma really says there are local coordinates in which I can write f. Of x and y as sum xi squared minus sum yj squared. And Euclidean then means that I can find those local coordinates so that I have this sort of Morse normal form, and the metric in those coordinates is Euclidean. Because once I have that, I have this picture. But it's not clear that this Morse lemma gives me Euclidean metric and right. Not every metric even is locally diffeomorphic to Euclidean metric, right, because we have curvature. So these are special metrics, and then one can go back in and prove that Euclidean Morse-Smale pairs exist. So And so I've already labeled things with unstable and stable manifold here. Let's try to actually define those. There we go. So, well, you see somehow all the green stuff here, everything that's on the y-axis converges into the point P, and forward time, and everything on the blue on the x-axis converges in backward time to the critical point P. And that's exactly how we define those. So it's the points for which the negative gradient flow at t equal to plus or minus infinity goes to my critical point P. And in the local coordinates, those are exactly the coordinate axes. Well, and they are, well, locally they're smooth submanifolds in this chart. And then globally, I simply get them by flowing with my smooth gradient flow. So they stay smooth submanifolds in my entire manifold M. Or I could say locally they look like disks, right? And then I can keep flowing them up to infinity. That, you know, they're never going to intersect because we have a, you know, vector field flow. So you will get, you know, sort of hyperplanes or planes embedded. The question is, of course, they're going to sort of wrap around other critical points. Right? So you don't want to compactify that here. So that's my unstable and stable manifolds. And one notion here is we like to call the dimension of the unstable manifold, so the dimension of the blue thing here, the index of our critical point. That's k, that's the number of negative eigenvalues of my SU. That's a choice. You might as well take the, well, that's the choice of whether we're going to do Morse homology or cohomology. Right. So, with that, right, so in the olden days, like Bott and then, you know, so Milner in his book, they used the unstable and stable manifolds to then get a CW decomposition and, yeah, understand the topology based on that. So what was sort of started with Witten was to instead look at the manifolds of Morse trajectories. So in the first go, that looks like a solution to an ODE. And there's, I like to think that there are actually 4 kinds that we should think about, where the 4th kind is one that we don't need for the PSS proof. But, so there are infinite flow lines, right, solving the gradient equation, and then they're kind of forced to converge to critical points at plus or minus infinity. We just keep track of P and Q here. Right? There are also half infinite. They're either infinite towards minus infinity or plus infinity, solve the same equation, and then in backwards or forwards time converge to a critical point. Right? But at 0, they're going to be just some value in M. That's what I mean by the first sort of entry being M. So these 2 guys here have an obvious, well, they have a, these are actually the stable and the unstable manifold of P. So let's see. So this goes in backward time to P, so that is the unstable manifold of P. This should be the stable manifold of P. And how do I get there? You know, when I have X, I simply evaluate it at 0. Same thing here. Oops. So, if I believe that the unstable and stable manifold were smooth submanifolds of my ambient space, then this gives these trajectory spaces a smooth structure. Good. And now I'd like to do the same thing with the infinite Morse trajectories. So here the problem is I'm actually quotienting by R. And that's the reason that I wanted to do this here. So I'd like to declare this as isomorphic to this intersection of unstable of P, stable of Q, and sort of the R quotient is the intersection with a regular value. And here, well, right, so for the more small assumption, I've only said, well, you know, I want this to be, okay, right. The good thing is if it's transverse in M, it's going to be transverse in all level sets. Right? But now I need to choose a level set to give us a smooth structure, so I should make sure that all those smooth structures are the same. Yeah. But all the regular level sets between P and Q, well, better be related by a flow. That's not completely true, because there might be other critical points in between. Right, but that's not where this intersection is going to happen, so there's a little bit of hand waving going on here. So really you'd like to be able, in order to sort of, you know, isotope the smooth structure, you'd like to be able to take any value between the two values of P and Q. So this intersection here is the quotient by R. Right. So that's why I say manifolds of Morse trajectories, because, you know, the data actually sort of induces a smooth structure on it. Right. And for shits and giggles, here's the last one, where I allow myself just sort of finite length Morse trajectories. And, well, there's a decision to be made here. It's kind of interesting of, you know, this could just sit at a critical point and be constant. The decision that I'm going to make is that trajectories of different lengths that map to the same point, have the same image, are still different because they have different lengths. So I'm going to declare this isomorphic to M times 0 infinity, right, simply by looking at the initial point and the length. Together with the flow of the gradient function, that gives me a bijection, and that's the smooth structure that I put on this. One reason I like this is that this starts as a manifold with boundary here already, right? So at 0 we have a boundary. And once we compactify, we're going to get more boundary, but more boundary is all going to sit at infinity. And so this sort of, the decision of sort of declaring Morse trajectories with the same image of a critical point different by the length sort of separates the two boundary components completely at length 0 from length infinity. But otherwise I would get some kind of weird structure near the broken, or near the, well, eventually there's going to be also broken curves that all sit completely constant at a critical point. So there's sort of a bit of a blow-up construction there that I like to talk too much about, because I sweated about that a lot at some point. Right. So these are the unbroken Morse trajectories. Right. So here they are again in shorthand, and now I'd like to compactify those spaces. And so I can do this, by taking any initial and any end, sort of condition, and then, well, the compactified space. Well, I should take the non-broken ones that I had before, and I can allow myself to start breaking. So, let's see. Right. So these guys here start at P and end somewhere within M. and I could simply break somewhere in the middle here. Or I could break several times at several critical points. Right? And the same thing happens no matter what my end conditions are. You know, here they parameterize sort of finitely, and the length could get larger and larger, and as it does, it could get close to critical points someplace in the middle. So let's get that straight, right? So that means I can break at any critical point m of green star to p, m of p to blue. Well, this here is blue. It's the green guy. And then I could break twice and 3 times and so on. Right, so here you already see that somehow in the compactification of this guy, in the first step I pick up the 2 half-infinite guys, and in the third step, or in the second step, I also need to get the infinite flow lines. Right, so if I just started thinking about this in compactified, I would sort of pick up those moduli spaces automatically. And oops. So further things is just, this is the first exercise in writing out full compactified spaces, because I think that's useful to be able to do and not just hand wave once we get to our holomorphic curve moduli spaces. So I can break k times, I have any number of points at which I break. Here's my long product. Of course, the question is whether that's finite. And so here, since we're in Morse theory, we know that, well, right, so here I need to crucially use this notion. I would like there to not be a trajectory from P to itself. So I guess what I'm saying here is that I would like these guys here to be non-constant. So in the both side infinite ones, I'm not going to allow trajectories that sit at a critical point. Because otherwise these chains could get infinite and they're really just meaningless. I could have like m of pp in between infinitely many times. I could still now sort of worry, how many points can I get here? And the nice thing with the Morse function is that the negative gradient flow goes down in value. And so since you only have hopefully finitely many critical points, you can't get back to any one. So you can at most break at all of them. So this will be a finite union. Still not clear that that's a compact set in any sense, right? So far these are all products of smooth manifolds. And it's actually disconnected because I haven't given it a connecting topology, which I'm about to do now. So the usual topology that you put on this is you just look at the images of the flow lines. You kind of add the critical points in, so you get closed subsets, and then there's the Gromov-Hausdorff metric on closed subsets of a metric space. So that's a decent metric. The thing is that right here, for the sort of finite length things, I need to add some kind of length, some piece of distance between different lengths, so I can tell those apart. Right? So there's an extra length thing that we're not going to need here. So, and with that, there's a Folk theorem that also has, well, at least for the sort of classical Morse trajectory spaces of just connecting trajectories of two critical points. The Folk theorem says these are smooth manifolds with boundary and corner. And personally, I don't like the word R in that. I've learned that when you talk about smooth structures, you need to be a little bit careful. Oops. Oh boy. So I like to instead say that these compactified, so these compact metric spaces are now Hausdorff, right? Because they're metric. So I don't need to say that again, but so I just need to give them local smooth structure, and I would like to say they can be given smooth manifold structure. And well, the way I decided to construct that is at some point to sort of define something that's called associative gluing maps. I mean, gluing means you glue together, you know, things that were broken at a point, you make them unbroken nearby. But if you have a long chain of if you have a chain, then you could sort of first glue these two and then glue them to this one. Or you could first glue these two and then glue them to that one. Of course, in each gluing, you have somehow gluing parameters going on. And the sort of buzzword associative means that with the same gluing parameters, you should actually get the same result no matter in which order you glue. That's something that, you know, for some of the harder applications of Morse theory, one would really like to have. So Ralph Cohen actually used these at some point, I believe, to sort of exhibit something like Stiefel-Whitney classes somehow for in Morse theory. Sorry? Ralph Cohen, who's at Stanford. But so my motivation for sort of using that was more that kind of asking these gluing maps to be associative, sort of that's what gives me sort of a canonical smooth structure on my Morse moduli spaces. If my Morse-Smale pair is also Euclidean. So I wanted to see how much of the smooth structure actually sort of gets seen by the Morse trajectory spaces. So we don't really need to know about that. What we need to know is, first of all, that the boundary, the true boundary, when I take the corners away, is just the once broken trajectories. And that the number of breakings that I have is in fact sort of the corner degeneracy index, right, where I sort of count how many coordinates are zero, you know, in my sort of standard quadrant chart for a manifold with corners. So that's nice. And the other thing that we'd really like eventually, because we're going to couple these Morse spaces with holomorphic curves, is we like evaluation maps. And I already used the evaluation map to make these spaces, like before the compactification, I made this equal to the stable manifold of P plus. And now I'd like to extend that evaluation map to the compactified thing, right? But that's really no rocket science here. So in this compactification, the first one is going to be finite length, and that's simply where I'm going to evaluate. So that's the notation here. You have, you know, a sequence of Morse trajectories, and you just evaluate the first one at 0. And similarly here, right, if we have sort of this is something in the, well, what happens here is I took the unstable manifold of P minus and I compactified it, but I didn't compactify it within M, right? Because there could be different ways of breaking and getting to the same sort of limit point. So I really compactified it sort of by adding these whole flow lines. And so, yeah, but so I'm supposed to just evaluate at the last here, right, 0. So that was maybe a little cryptic. Let me try to, right, so this is xk of 0. And here's P minus. Right, there could be different ways of getting from P minus with a broken flow line to xk of 0. In fact, they could even break differently often. And if I compactified my unstable manifold within M, then I would declare right. Then I would declare this, well, there's something really weird going on, right, because the unstable manifold somehow of P minus, right, it's just flow lines that go into P minus. So this part is a bit of that, and that part is that. And everything that is unstable of this critical point is never in backwards time going to flow into P minus. So these extra black lines are actually totally not part of this unstable manifold. P minus. So it just takes up everything here. And so the sort of the compactification adds the sort of, well, and all of these points go into the compactification of the unstable manifold here. So do these. But the thing is that this point here now becomes 2 points in the compactification, depending on whether I got here this way or that way. So this is not equal to the closure of P minus in my ambient space. Anyways, so that's just, it's sort of, well, maybe it's an analog of Gromov compactification, right? We made a choice of how to compactify here, and we in particular, we did not take the obvious ambient space and took the closure in that. And that's what Gromov compactification also does. It doesn't, have an ambient space and takes a closure in that. In fact, it's not. This is a compactification, right? The unbroken ones are dense in this. I've decided that I should probably start calling it Gromov compactification, because it's not, it doesn't contain the smooth curves as dense set necessarily. But here we're in luck. So, questions on Morse world? Yes.
The picture on that X0 can be a critical.
X0 indeed, yes, that could, this whole thing here could sit at this critical point. Yes. I do want that. So, good. All right. So, with that, we have the language to go back to our minimal proof of the Arnold conjecture. Right, so Now that I've properly defined that, I can say that I want a Morse-Smale pair, and oops. Geez, there's something bad going on here. Ah, there. Oh. And I want to prove the non-degenerate case of the Arnold conjecture, so I take a time-dependent Hamiltonian and I look at my periodic solutions. Because it's non-degenerate, I know this is a finite set. You know, they're cut out transversely. And I'd like to prove that they have, that there's at least as many periodic orbits as there is, you know, Morse homology or fractional homology. And, right, for that purpose, I first take an algebra refresher and somehow define my Novikov ring, lambda, which we'll get to in a bit to see which one we actually need. Just for the Morse differential, that's really not important. Right. Here, oh yes, there's one thing I didn't say about the Morse trajectory spaces. I guess, right, that's the nice thing of the index here. Right, so as I describe this connecting trajectories from P to Q, this will have dimension, right, the dimension of the unstable manifold minus the codimension of this. So I'm going to get P minus Q, and then I need to subtract 1 from, well, the quotient by R of this intersection. So that's a good dimension formula, and with that I can now say what it means to just count the zero-dimensional part. Right, I'm just going to, here I can simply restrict the index of the critical points that I want to sum over. So, well, d squared is 0, the Morse homology is equal to the singular homology. And now I'd like to construct these 4 maps that somehow factor an isomorphism on the Morse homology through the periodic orbits so that I get a lower bound on the number of periodic orbits. So, right, so the construction of all of these maps is going to be the same kind of formula. There's a dot and a star, and I need to look at moduli spaces between star and dot. Oh boy, this might be the wrong way. I probably want to go to, oh boy, from dot to star, and then I want to get, oh no, sorry, from, oh, this was right. Never doubt what you prepared. Oh wait, here, sorry. Right, I want to map star to something. I'm going to, sum over all the possible outcoming markings. I need to tell you what the zero-dimensional moduli space is, and then if I'm lucky, I can, sum over it with some weights, and I also need to tell you what the energy function is. But that's, so, that means really, in order to define these maps, I need to tell you what the moduli spaces are and the energy. Let's see. Here is, well, I guess lovingly called that a piece of bacon, right? So this kind of picture here, how can we get that? I want to think of this piece of holomorphic curve as parameterized by C, because there's an infinite end here. And then there's a weird d-bar equation going on. But the advantage of talking about it as C is that I have a 0.0, and I can simply ask for that to lie on the unstable manifold of P, right, which means I flow from P into here. That's a way of saying that's there without having to add sort of the data of the Morse trajectory as a solution of an ODE. And I'll always want finite energy. So what's that weird? The weird equation here comes from the fact that really what I would like to think of is certainly out here I'd like to think of cylindrical coordinates. So I'm simply going to do that by mapping c minus 0 to the cylinder. Right, by what do we have? E to the, and I want to get S1 to be sort of 0, 1 mod z. So I'm going to take 2 pi s plus it going to s and t. And in those coordinates I can talk about, in those coordinates I would like to say that I solve an equation for maybe v equal to, what is that? U maps from here to someplace, so I need to compose that with theta inverse. So that I would like to have solved dsv plus j dtv equal to, well, towards plus infinity I would like it to solve j xh of v. But near minus infinity, I'm going to need to fill in. Oops. Right. So here's your cylinder. At minus infinity, I'm going to want to fill in the point 0 to get to this kind of picture. Right. So I need to somehow use removal of singularity for pseudoholomorphic cylinders with finite energy. So I need to somehow cut off my perturbation on the right-hand side. So that's your cutoff function. That's actually supposed to be equal to 0 down here. Right. So maybe I should. Can I move that? No, I can't. So this is equal here, right? So theta should be 0 out here, 1 up here. That way I have sort of the d bar operator unperturbed. Yeah, out near minus infinity, near plus infinity, I just have the Floer equation with the h in the equation. Right? And so then I can sort of rewrite this. I can, this now one can pull back with that map, and so that's what I mean by, pulling back this vector field. Except that's a 0-1 form. This was just a vector field, so I need to sort of 0-1ify it. So beautiful notation for that somewhere in McDuff-Solomon, and they talk about symplectic vibrations or Hamiltonian vibrations. So that's all. That's a completely legitimate perturbed d bar equation now on C. And I can think of it in these two different ways. It's just when I now make my Fredholm theory, I need to decide whether I'm going to use Sobolev spaces on C or Sobolev spaces on the cylinder. And they can be slightly different. So next thing, I need to tell you what the energy is. Oops. And, well, I think there's a bunch of choices that you could make here. I like this choice of taking the symplectic area and somehow adjusting it by something that looks like a piece of the symplectic action functional for h. So this is just integrating out here near plus infinity, or at plus infinity. The reason I like this is that this is a homotopical identity. So if I homotop U with fixed limits gamma, I keep getting the same answer. And the other reason I like it is that I have my energy identity. Well, yeah, there's a little bit of pesky stuff going on with this cutoff function here, so I need to be careful when I get my energy identity. So I get, if I go back to V and integrate over the cylinder, I get the integral of dsV squared, but I get some extra stuff. But fortunately, I can throw the S derivative on my cutoff function, right, which is supported, oh goodness, positive derivative or positive derivative, right? So ds beta is something like this. I can make this, compactly supported, and I'm composing my Hamiltonian in this little piece of area with V. My Hamiltonian is uniformly bounded since I'm on a compact manifold. So this is a quantity here that I really can't control, but it's bounded by some uniform constant that just depends on my choice of beta and the function h. So that's good news, because I would like energy bounds to give me Gromov compactness. So this means energy finite is the same thing as integral dsV squared finite, and that gives me, I can now run my compactification construction of looking at bubbling points, and then on the complement you get uniform bounds on this and can run elliptic regularity. That's the good news. The bad news is this thing here is not necessarily positive. So I could have my energy negative, but it's at most some fixed constant, right, again, that I get from this. But C0 is fixed once and for all. And so that tells me that when I now go into this kind of equation, and I'd like this to give me something in the Novikov ring, I'd better allow negative exponents. So this tells me, really, the geometry, or maybe the analysis here tells me which Novikov ring I should take. So it's in fact the, I believe, Novikov field. So I'm still allowing myself rational coefficients, and then the EI's I would still like to be ordered. I'm not asking the first one to be non-negative. I'm also not going to ask it to be bigger or equal to that C0, because then somehow that Novikov ring would depend on H. It's just going to be finite because it's a real number. And as people observed last time, I actually do need EI to go to infinity. It's because there's the other definition of the Novikov ring or field is to always say, if I truncate at a fixed energy, I only have finitely many terms. And somehow I was under the impression that that's equivalent to just having ordered energies. But it actually also truncating and getting finitely many terms also means that if this is an infinite sum, right, the energies actually have to go to infinity. So, right, so that's what our lambda is going to be. It's simply because we want to get, we want to evaluate there. So, question? All right. So, long story for this one moduli space, right? So that was PSS here. But now SSP really doesn't look much different. So let me do the brutal thing here first. Right, so SSP should just have an incoming gamma and an outgoing P. And that means I would like to kind of just reflect these pictures here. So I could do that by just making a conformal change here by just flipping both variables. And then I believe I want 1 minus beta in the whole thing here. So, right, this will be a different theta. Instead of beta, I would take 1 minus beta. And then instead of landing on the unstable manifold, I want to land on the stable manifold. So, not much happened. In particular, well, one nice thing is that this sign here is going to change. So, eventually, when I glue them together, it actually didn't matter whether I decided to add this quantity or not. When I add the two energies, right, I'm going to want to glue these. It's going to cancel out. And I'm still going to have that whole argument here. So PSS and SSP, not much different analytically. So here is the full glorious PSS and the full glorious SSP, which really, doesn't look much different. So I'm just getting my pieces of bacon the other way. So that means, well, so now I could tell you what I is, but really I is going to be the other boundary component of a homotopy that I start at the composition of these two. So I'm just going to tell you what H is first. So let's see. So H, there's sort of a forceful breaking going on. I'm going to let, a length parameter R go to infinity, and for finite R, so the BIM, they all look very similar now. So for finite R, right, I'm going to have glued my things together, so I'm going to see a CP1. There's going to be one mark point that evaluates to the unstable of P minus, one that evaluates to the stable of P plus, finite energy, and I need to pull back some kind of equation from the cylinder, which I now get from taking 2 points out of CP1. So, picture is this. Right, so here's the cylinder. I take a bump function that's sort of supported on the interval minus R to R, and there's maybe 1 on the interval of length 2 less. So somewhere in the middle I actually have the Fleur type equation. Near the ends I have the unperturbed one, which means I can again run removal of singularity and think of this as a map from CP1. Because that then gives me the 2 marked points here, 0 and infinity, at which I can ask for this to lie on the right plot points. And right, again, I kind of just need to pull back this perturbation from the cylinder to CP1. That's R equal to finite, right? And then for R infinite, I would like to glue in the, so this is R equal to infinity here. I would like to add the broken curves, right? So a PSS and an SSP here. And I'm usually, well, I'll probably stop keeping track of the J here. Right now it's kind of important to have the J here to say that these are actually holomorphic curves and not just Morse trajectories from P minus to P plus. Okay. But once I break here, if it goes from P minus to periodic orbit gamma, there has to be some holomorphic curve in the picture. So there's already some kind of gluing going on, right? These are all sort of cut out of the same Banach manifold of maps from CP1. And in some limit, well, I have 2 maps from C. But we can again write down an energy here. And as promised, I would like my energy on this here to simply be the sum of the 2 energies of the sort of PSS energy of U minus and the SSP energy of U plus. I realize that's going to get rid of the limit term of the sort of symplectic action at the breaking orbit. And really, if I glue homotopically, the 2 maps actually are going to get glued. So this tells me that my energy at finite R, I should just take the symplectic area of that sphere. But then again, I have the problem that this is a perturbed d-bar equation, so I get some extra stuff. But again, the extra stuff is bounded. So nothing too terrible. So that's H, right? That has sort of, well, we're going to expect it to have 2 boundary components, one at R equal to infinity. That's this one. It's the one we like. And then one at R equal to 0. That's what is going to define our map I for us. Okay. There we go. Right. So that's simply going to be the R equal to 0 part of these I moduli spaces here. Right? So if you set R equal to 0 here, then my cutoff function here will have absolutely no support. So it's just simply going to be 0. So I just have d bar U equal to 0 on CP1. I still have my 2 marked points. And I can ask for finite energy. And the energy is still, U star omega. And then now this energy is actually non-negative. So this, I know, is actually the integral. Maybe 1/2 du squared. And that's the place where I'm going to want to argue with upper triangular things. So that's a good thing. There's a whole industry of what you can still do when you have these extra things, right? So here, if you stare at this, we often like the energy to be non-negative to run some kind of algebraic arguments, and that's fine as long as my Hamiltonian happens to be non-positive, non-negative, non-positive, right? If H is less or equal to 0, then this is going to be a, oh no. No, it's not, because, right, so the problem is that ds beta is positive here and negative there. So I can't make this up with H. So there's all kinds of subtleties in, how might my Hamiltonian change over, certain areas. So this is, there's science in this. in other settings. So, right. Note one thing here. Right, so this moduli space has an extra action by R times S1, which is, you know, the automorphisms of CP1 with marked points 0 and infinity. But we're not quotienting by it. Simply because it's the boundary of a moduli space which does not have that action, right? So these guys here don't have the R action because, you know, the cutoff function isn't R shift invariant, and they don't have the S1 invariance because usually my Hamiltonian isn't S1 invariant. They do have an S1 invariance if H is autonomous. And that's what has gotten used a whole lot to prove the Arnold conjecture, and our goal was to not use that. So we will not worry about that, hopefully. All right. Good. So we have a whole lot of moduli spaces. Right. And now it would be awfully nice if we could prove that, in fact, you know, this composition is equal to I on homology level. So, and this is where my preparation waned. So I didn't know what to cut here, and I don't want to write this all out. So let's go through this here. So first, step one was to make the Morse complex with Novick coefficients. Right, so step two is to actually make these things well defined. They're a little bit different. So the first three were all cut out as, you know, a single Fredholm section, you know, from a single space of maps, because they all had the same domain. They were all d-bar minus some kind of zeroth order operator, for example, you know, one of these pullbacks of Hamiltonian fields, right? There's no derivative on U. It's very nonlinear, but it's zeroth order. So then piece of notation here is we're going to, you know, K subscript K will be the Fredholm index K part. And here this is actual Fredholm index because there's no quotienting by groups going on, so this is all somewhat easy. Then the H is a little bit different, because you take sort of, this is all a family of Fredholm operators. So here, sigma R is a family of Fredholm sections over a fixed Banach manifold. Well, for R less than infinity. Right, so you can think of this as an equation in sort of the reals times that Banach manifold. But then you have to glue in R equal to infinity. And at R equal to infinity, we just have this, well, fiber product of the PSS and SSP spaces over, you know, the periodic orbits. This is a pair of Fredholm operators. Right? And so we talked about how that can give us, you know, sort of smooth structure near the broken things by this gluing analysis. So now when I write down 0, I mean the stuff of this big space that I expect to be zero-dimensional, which means when I look at the Fredholm index of a fixed R, it's going to be index -1 of this You know, there's going to be a d-bar operator also. It's a perturb d-bar operator with perturbation depending on r. If I fix the r, the index of that d-bar operator is -1, because that means the map r comma u going to, you know, the d-bar operator of u will have index 0. Right? Simply because what I added was the r in the domain, which adds adding like one dimension to the kernel. So, right, that's a good thing, right? So we expect somehow when this Fredholm operator is transverse, we expect no solutions. However, in a family, you're not going to stay transverse. At some point, you're going to have solutions. So, in some sense, this zero-dimensional moduli space here really counts the non-transverse solutions that happen, but only the ones that are bad with index -1. So the least bad non-transverse solutions are getting picked up here. And I don't have to add the glued things here, because we're going to hope and assume that both of these are cut out transversely. So there's not actually any bad solutions at this end. Differently put, when I look at sort of virtual dimension, let's go up one dimensional bit. Here I would like to see index 0 for every single time. And then it makes sense to look at index 0 times index 0, for the broken ones. So there's an index additivity here, right? 0 plus 0 is 0. So if I wanted to have sort of broken things in the previous one, at least one of them would have to be -1. But we're assuming that to be transverse, so it shouldn't happen. That's why, well, yeah. These are not the compactified moduli spaces yet. These are just the, hopefully, smooth ones, if our Fredholm operators were all transverse. And so that's the dream now, right? So the dream is I have a dream. What colors are dreams? Pink. Oops. No, that didn't work. There. So the dream would be that I find one almost complex structure on my symplectic manifold, so that at least up to index 1, all of these moduli spaces here are cut out nicely transversely, and the gluing works for H, and there's no bubbling, like sphere bubbling, that I might have to deal with. Sphere bubbling I might be able to exclude, you know, if the J also makes all holomorphic sphere moduli spaces transverse, and if the gluing is sort of transverse enough, then gluing in spheres says they're codimension 2, but I only have dimension 1. So yeah, it's believable, right? This is really what we expect to be able to do if we have enough injectivity of our curves to find this regular J. So let's assume that for the moment, right? So this eventually will need to get replaced by abstract theory or some abstract regularization. But if we're lucky, then somehow after that abstract regularization, the proof is going to read very similar, if we're lucky. So we would like to, right? So then all the moduli spaces are actually of the dimension that their Fredholm index is, right? So the 0 parts will be 0 manifolds. The 1 parts will be 1 manifolds with boundary. But let's see what we get out of the 0 manifolds. We don't necessarily know compactness now because we haven't fixed the energy. But when we fix the energy, to be less than some E, we get compactness simply by Gromov compactness. This is where we needed to know that sphere bubbling didn't happen. Because a priori sphere bubbling could happen, but it wasn't part of this moduli space. So to get that compact here, we need to exclude that. And that exactly means that I can cut this moduli space into, well, not necessarily connected, but components on which the energy is equal to some numbers that, go off to infinity. Simply, in this case, it's really clear that the energies are, quantized simply because I only have finitely many points. And if that is so, then sort of this sum over the moduli space with weights, I can simply rewrite as counting the number of solutions with a fixed energy, Q to the EI. And then this nice condition here of how my possible energies go up to infinity exactly tells me that I end up in the Novikov field as I wrote it. So when I write number here, I mean, counting with orientations, and I'm not going to try and say what that really means. It just means the AU. Every U comes with a sign. This would now be plus or minus 1. So that's a signed count. So this gives us well-defined maps. And just to get you possibly a little bit prepared for the abstract theory, I can think of this sum here, particularly if it goes over a zero-dimensional thing, as an integral of the function q e to the u, right? The map that takes u to q e to the u is a map from my zero-dimensional moduli space to my Novikov ring. And what I'm kind of doing here is I'm integrating a Novikov field valued function.
In Z mod 2.
I could work in Z mod 2.
Why is the fixed energy there's only one?
No, every solution U will come with plus or minus 1.
Okay.
Right? But when I sum, I might have several ones. Yes. I mean, eventually it could be a half solution, right? Just because it comes from some sort of multi-valued perturbation, but we're not there. So, differently put, there's a map from my moduli space to the Novikov field, and I'm kind of pushing forward the fundamental class. I feel a little uneasy about this because I don't know that. I think to push forward, you kind of need continuous maps. This is probably continuous, but I don't know that the Novikov. I mean, eventually, what I'm going to be able to do is sort of construct the virtual fundamental class as a check class. So that's maybe a question for the algebraic topologists here. Can I push forward a check class, a zero check class with a map like this to a Novikov field? Yeah.
Usually if you have like proper map.
I can push forward with a proper map.
Cycle is fiber-wise properties.
Yeah. Right. We should look at that. And that's not going to be the end of my worries. Eventually I'm going to need to think about sort of this being maybe well-defined up to some sort of one cycle. And so I'm going to need to sort of push forward one cycles with two different boundaries. So in the Novikov field, that doesn't seem right because the Novikov field is a little too discrete to really have one cycles between different things. So we might have to go back to this kind of notation with fixed energies. So right, that's my dream proof. Well, this is, defining all my maps, right? And then I go one further up. Well, so in two cases I'm going to go to dimension 1 for both I and for H. Right? So for I, I'm expecting the one manifold. And, well, what kind of boundary could happen? Well, now I'm kind of cheating. I haven't actually... This is not boundary, actually. These will be ends. Right. How could I diverge here? I said I'm assuming there's no sphere bubbling, so the only thing that can happen is that the Morse trajectories can break, and they can break in one or two ways. I'm expecting generically them to just break once. Right? I'm expecting to run to the boundary, not to a corner of with my evaluation map. And right, so here's I and a Morse connecting thing to P plus, or a Morse and then I, and summing over the ends gives me the equation that I is a chain map. And that was the warm-up, right? So H is a little bit different. So now I actually have boundary at r equal to 0 and at r equal to infinity. But I'll also have ends from breaking. Yeah. But again, I'm assuming that there's no sphere bubbling, so this is all that can happen. And as I sum over all the boundaries, terms, and ends, right, I have r equal to 0, which is I, r equal to infinity gives me this composition of the PSS and SSP. And here I have DH and HD again, which is now telling me that there's a chain homotopy equivalence between these two maps. Right? And so together, the consideration of the one manifolds tells me that, well, I is a chain map, and so together with this, that also means that SSP composed with PSS is a chain map. It doesn't necessarily mean that either one of them is a chain map to the Fleur complex, because I haven't even said what the differential on the Fleur complex is. Right? I don't need that. The two maps are the same on homology. Right. So I actually have this diagram now, and then I'm left with saying that I on homology is an isomorphism. And that, I think, is the argument we already went through. Right? By saying, right, so now my energy is positive or non-negative. So I have energy 0 parts, which simply have to be completely constant. They give me the identity part in my map. And then everything else has energy bigger or equal to 0. So, right, there are so my moduli space is the constant ones plus something non-constant, but the non-constant things have positive energy, so they'll give me something upper triangular, and then I need to go do my algebra homework to check that that is invertible. Hallelujah. Right, so that would be the end of a proof, if there wasn't all kinds of bad stuff happening. Right. So, bad stuff is for next week, but because this is so bad, we're not going to do it on Monday, because I'm gone, so we'll do it on Wednesday. Right. But I'll upload this, so if you guys want to get prepared for bad stuff, you can look at bad stuff and convince yourself that this is really all that can happen. Right? So the important exercise here is to not forget some kind of bubbling and non-compactness effects. All right. And then we're going to deal with this.